over these problems, I'm not going over them like it's the first time you've seen them. What I mean is I might go a little quickly. Now, if I'm going too quickly, or you're like, hey, can you go back to that? Just ask. But some of this is just me kind of saying, hey, do you remember this? You might need to still go back, watch the video that I'm recording, or maybe you just want to look at the answer key that I'll post to make sure you process, oh, that's what he was doing. But I just thought if we can say something, if we can kind of do this together, it's a good starting point. Okay, so we're going to start here in Unit 6 with function composition. Now, function composition is like g of f or f of g. I hope you don't think that it's backwards, but when you see g of f, it's actually the f that's getting plugged into g. Again, it's not supposed to be backwards, but that means that this 2x minus 4 is going to get plugged in over here for x. Do you see the way that it's going to look? Do you see that it's going to have a 7 and then a parenthesis with a square? But in the parentheses, we will place f, or what f equals, 2x minus 4. And it's a pretty good start to realize that that's the setup. I'm not going to lie to you, there's some algebra that is coming. 2x minus 4 squared, that's like 2x minus 4 times another 2x minus 4, which that's its own party there, trying to multiply those together. Don't lose the 7, but when you multiply or FOIL that stuff out, you get 4x squared, you get a minus 8x, and then another minus 8x. That's why you get minus 16x. And then you get a plus 16. But still, the fun's not over because you have to multiply everything by 7. So when it all shakes out, we have a 28x squared, a minus 112, I believe, and a minus 112x, and then a plus 112. Function composition, plugging a function into a function. In this case, we plugged f into g. Increasing, decreasing. Now, what I thought we would try to trigger here is that this is a graphing problem. You need to see a graph. How are you going to see a graph? Well, Desmos. You'll be able to use Desmos on the final, but do you know when to use it or why we're using it? Again, I need to know what this graph looks like so I know when it's going up and down. Now, it's going up and down according to that little zigzag. When you look at that graph, though, you want to be sort of noticing these maximums and minimums, because these are the places where the graph changes from going up to down or vice versa. So it's all about x values. Remember how we talk the talk? You use x values. Now, I forgot to switch this, so in the meantime, I drew a graph on my paper. I drew a graph, and I labeled the x values, because again, that's what it's all about. Now, do you see the graph going up? Remember, it's going up from left to right in both of these blue sections. That means it's increasing from negative infinity to negative 1. But it's also increasing from 1 to infinity. You have to give the answer the right way. So it's increasing in the blue sections. It's decreasing in this red section in the middle, which is from negative 1 to 1. Now that's not a point. That's an interval, negative 1 to 1. By the way, I thought we would go over problems that maybe are a little harder or are ones I would think you might forget. I'm purposely picking out some of those problems. Okay, there's probably plenty of things that you already remember. So what's up with this vertex thing for number 3? It's all about shifting. I'm trying to get you to realize when you're inside the parentheses, that's a horizontal shift. Specifically, it's a shift that's really messy. It's a shift with a minus sign. Remember, it's a shift to the right. Because again, it's a minus sign, it's a shift to the right. When you have this minus sign on the outside, it's a shift up and down. Specifically with a minus sign, it's down. So if I shift it to the right and I shift it down, then my vertex is going to match in that same manner. So it would be like a plus A because I shifted to the right, and it would be a minus B because I shifted down. A little harder, but we're using A's and B's to describe shifting. Domain. It's sometimes about thinking about numbers you can or can't use. When you have a square root, there's something special about that piece that's under the square root. It's not allowed to be negative. Since it's not allowed to be negative, I'm going to make sure it's greater than or equal to 0. If I make it greater than or equal to 0, then all I got to do is solve it. I hope you're going to add 4. And of course, when you add 4, you get greater than or equal to 4. Well, that's your domain. You can leave it like that. You could also say 4 to infinity if you were going to give the answer as an interval. But the bottom line is it's numbers greater than or equal to 4. Now, another way that we did domain was by looking at a graph. Yes, you'll be able to use Desmos. Not every question is Desmos helpful, but if I decide to graph the opposite of the square root of x minus 4, I get this little guy over here. Yes, it's going down, but what's more important is that it's going to the right. Since it's going to the right, it's greater than 4. So we could use the graph to kind of come up with the same conclusion. Next unit was on systems and matrices. I'm not able to go over everything right now, but I thought I would pick out something that might need some reminder. Multiplying, remember? It's this row times column method. Now, when I circle the row and the column, I'm going to multiply the matching numbers. That means 3 times 2. That means -1 times 6. Now, when I multiply those numbers, I then proceed to add them together. The technique is called multiply add. And maybe that's something you write down on your note card someday. Multiply add. Now, I still need to multiply and add the next row. I notice that I'm using the same column, but I'm going to now use the next row. That means 3 matches with 4, multiply to be 12. -1 matches with 7, multiply to be 7. And if you add those, okay, and then the fun starts over. You continue to multiply and add, that is, circle a row and a column. Now be careful, 0 matches with 2, and 2 matches with 6. So it's 0 plus 12. And if you kind of want to do some of this on your own, you're welcome to do a little circling and multiplying and adding. She gets 0 plus -14. Whoops, 0 plus -14. And how'd you do with the last one? Careful that your eyes are looking at the correct matches. I'm happy to talk about it, or you can just check your answer. Remember, you can always rewatch the video if you want, or check the answer key that I'll supply. Determinants. Again, do you remember? Sometimes just hearing the word, it's like, oh yeah, determinant. Determinants, it's a different idea. You multiply diagonals. You multiply diagonals. And then you subtract. Determinants require subtraction. And that's what's going to equal 10 just because this problem says so. So I multiply the diagonals, but I subtract, of course, in the right order, and that's why we get x equals 2. Now there's other things in that chapter which you'll find on the back of the paper, but I'm going to move into Unit 8, which was on polynomials. Now when you read that problem there, all kinds of sort of technical terms, degree, cross, touch, goodness. Honestly, this is not necessary for this problem, but I'm doing it anyway just to add some information. Because remember, if I know that there are behaviors, we call them behaviors, on the x-axis, further, if I know that the graph crosses but touches, I can actually visualize the graph. Now, nothing in this problem required me to draw a graph, but I thought it'd be helpful if we just remembered that. But if 4 is an x-intercept, then x minus 4 is a factor. Likewise with x minus 1. But remember, if you touch the x-axis, it has to count twice. So that means I get x plus 2 squared. I get x plus 2 twice. Now, notice I don't need to multiply that out. It didn't say I needed to, so I'm just going to stop there. But what's this degree thing, degree 6? Remember that the degree is supposed to equal the total number of roots. The total number of roots looks right now like it's only 4. So where's the other 2? Well, they would be the imaginary roots. Again, there's 2 imaginary roots because I already have 4. And of course, if you add them together, you get 6. Okay, so we just kind of deduce that based on what is given. Now remember, if I'm going too fast or if you just want clarification, just ask. Because I am purposely trying to go over a lot of things. I also don't want to frustrate you by doing that. All right, so solving a polynomial. Now there's all kinds of ways to solve a polynomial, but this one looks like it's kind of screaming factor. So if I factor it, factor out an x, good luck. If I factor out an x, then I can find the roots. Now, don't forget about this x out here, and good luck to you too. That root, that factor of x is going to produce one answer, the answer of 0. But this one in the middle, now that's a different story. That one in the middle is going to require the quadratic formula. I'm not going to go over the entire quadratic formula. Maybe you want to write on your note card. It's the opposite of b, plus or minus. Now don't forget it's square root of b squared minus 4ac. If you do that carefully, you get the square root of 24. Again, I'm kind of skipping to that. Now it's a multiple choice test, so unfortunately you can't get any partial credit, but what I'm suggesting is that the square root of 24 needs to be simplified. I'm sure that the answer on the multiple choice test is going to have the square root of 24 simplified by thinking a little bit about, well, some perfect numbers. Now that red 4 right there is perfect. It's going to come out, and it comes out as a 2. Now when it comes out as a 2, it leaves behind that 6, the square root of 6. We're not done yet. Everything's being divided by 2, which is perfect for cancellation. Be careful though, when I divide by 2, I actually left with the number 1. I'm left with the number 1. Except, whoops, not except, but it's 1 plus or minus root 6. Now, don't forget about this 0 out here, because technically there's 3 answers on the screen. 0 and 1 plus or minus root 6. Oh, well, we should have got 3 answers. Remember, your polynomial was degree 3. Degree 3 is the exponent, the highest exponent. Dividing. When you synthetically divide, you actually divide by a number. Not negative 3, but 3. You divide by a number. Then you put the coefficients down. the coefficients of your polynomial, except the x squared is missing. Since the x squared is missing, I put a 0 in its place. Now remember how to synthetically divide. Maybe again, it's something you put on your note card, because the method is to multiply and add. Multiply and add. I even got myself mixed up there. So I multiply 1 times 3, but then I add to get 5. I multiply 5 times 3 to get 15, but then you add and you still have 15. How you doing? Are you multiplying and adding? 34 times 3, a big old 102. That's kind of weird. I get a remainder of 42. A lot of times you get a remainder of 0, but who knows, maybe on the test I'll just ask, what's the remainder? And again, the remainder is 42. Doesn't always have to be 0. Remember, this guy right here is called a depressed polynomial. It's depressed by 1 division. Continuing, we have an equation. Not exactly like one on your mini check a moment ago, but are you kind of feeling that it's the same idea? You basically isolate. So I'm dividing by 3. And once I isolate, I then have to do something to get rid of this little 3. That little 3 is called an index. And what I want to do is I want to do the exponent that will get rid of that index. So that big black 3 is going to cancel with that little red 3. You get 27 to the 3rd power. It's a big old number, 19,000, but that's what you get, 19,683. But the main thing was that I did a power to both sides. Well, you just got done taking a quiz where you might have used like a reciprocal power. It's actually the same idea. This equation, however, does not use powers. It uses what's known as an LCD. Now, the LCD is going to have all the factors represented. That means it's going to have an x and an x minus 3. That's called the LCD, and then you multiply it to each numerator. Now, I'm going to just write it down to save myself a little bit of space. I'm just going to multiply the x minus 3 to each numerator. Remember, that's called the LCD, and it had each factor represented. Now, the cool thing here is that I can go to the business of canceling the denominator. So x minus 3 cancels, x cancels, and x minus 3 cancels. Of course, you got to keep track of what's left. Okay, what's left is still a 4x. What's left is a 3 with an x minus 3. And what's left is a negative 2x, but with an x. Don't forget that single x. Now, you kind of have to see a little bit into the future that this equation is going to be a polynomial. What's that? It's going to have like an x squared. Specifically, it's going to have a 2x squared. I need to move that over to the other side because I don't want to have a negative 2x squared. So I'm going to add that over to the other side. Now, a 4x and a 3x are going to add to be 7x. That's just in the middle there. And then you also get a minus 9. I did a little bit of distributive property all in one step there. This thing is a trinomial. It's equal to 0. Yes, you could use the quadratic formula, but it just so happens that it can also factor. It's a tougher one to factor, but since we're together, we could eventually arrive at these 2 factors. Remember, we're doing this so that we can solve for the zeros. You end up with negative 9 halves and 1. LCD. At the very beginning, this circled guy right here, it used all the factors. It didn't overuse them. It just made sure that each one of them was represented. Again, it's called the LCD. Lots of math that you have learned. Maybe we should rename the final a celebration of learning. Sounds like a great idea, a celebration of learning. Moving on to asymptotes. Now, we're getting into some things that hopefully are a little more recent, especially since we spent so much time with asymptotes. But do you remember? We have a vertical, a horizontal, and, well, maybe a slant. Now, the vertical asymptote is going to come from the denominator. The denominator equaling 0 is, of course, a bad thing. Well, that happens when x equals negative 1/2. Sure, it's a fraction, but x equals negative 1/2 the denominator. The horizontal asymptote, there were some rules, right? I mean, do you want to write those rules down? If you compare the numerator, you would realize it has an x to the 0. If you compare the denominator, you realize it has an x to the 1. Bottom line is the top is smaller than the bottom, which means the asymptote's at 0. But there's a shift. There's a shift of +2. So we ultimately arrive at 2. There's no slant because, well, the top is smaller than the bottom. But maybe there's something over here. Maybe there's a vertical, a horizontal, or a slant. Okay, now again, the vertical should be pretty easy. It's all about the denominator. -2 is that bad number. There's no horizontal asymptote because this time the top is greater. In fact, it's 1 greater. Remember, if it's 1 greater, then there is a slant. Now, how do you find a slant? You have to divide. Did you have to? Yes, we're going to divide. Okay, this one requires long division. And, well, I can get the ball rolling by looking at those first terms. 5x times x is 5x squared, and then 10x. And then we're doing, of course, subtraction. Now, when you do subtraction here, make sure that you're subtracting both of these, which gives you a -7x. Now, that -7x is honestly the last number I need so that I can write down -7. Technically, y equals 5x minus 7. Okay, that's your slant asymptote. Y equals 5x minus 7. I stopped because I know I'm going to get a remainder. How are we doing here? I still have a few minutes, right? Let's talk about a hole in the graph. Now, a hole in the graph comes from looking at the numerator and the denominator. I hope that when you look at the numerator, that you feel like it can be factored. It is basically the little trick that you have to factor it. And once I factor the numerator, it makes it more clear that the denominator, well, the numerator and denominator share an x minus 4. Now listen, as soon as I see that that x minus 4 is shared, I know that there's a hole at 4. But remember, we want to give the answer as a x and a y. So I cross off the x minus 4, kind of temporary, and I end up with x plus 2. Okay, good luck. So I end up with x plus 2. Now, x plus 2 is a safe little version of this original fraction. Why do I say it's safe? Because I can plug in the number 4 safely. And when I plug it in, I get a y value. I get 6. And that 6, again, is the y value that makes my complete answer. It makes the complete answer to be 4, 6. And then if we're going to write an equation, then I kind of have to build my fraction. Remember, when you build the fraction, most of the time you build from the bottom up. That is that you want to think about the denominator, x equals 3, x minus 3. Now that's in the denominator. Getting the horizontal asymptote, you have to do a little thinking about the numerator. Now, if you like the number 4, maybe you'll put that in the numerator. Problem is that that's not going to totally get the job done. I'd have to write it as 4x. That way I have my degrees equal. Now, if you don't like 4x, maybe you want to go another route. Maybe you want to put like a 1 up here. If you put a 1 up there, that's fine, but now your asymptote's at 0. Just shift up 4, and you'll now be at 4. There are some different options. It's a multiple choice test. I'm not going to have more than one right answer, but both of these could be the right answer depending on, again, what you see in that list. Do we still have some time? Again, I know that maybe you got to look back at this. Maybe all this is doing is kind of reminding you of what we've done, but we arrive at Unit 10, which was, it's more is the unit that we just finished or we're still kind of working on. But here I see a root. Now, a root can be interpreted as a denominator. I'm talking about the denominator of the exponent. If I want to, I can write this as 27 to the 2/3. There's also a version when you are looking at variables where you would split your x into some perfect x's. That is an x to the 3rd and an x to the 1st. Now, the reason I split it into x to the 3rd is because that's the highest amount of x that's inside of that x to the 4th. And so all of that x to the 3rd can come out, and it comes out as an x. It leaves behind the red x. Again, the blue x came out because I divided. The blue x came out because I divided. Now, back to this 27 to the 2/3, I still should simplify this. Why don't you find the 3rd root of 27? That's 3, because 3 times 3 times 3. And then I can square, and that'll end up being 9. So when I take care of 27, I end up getting the number 9. And then I did all this stuff with the x, which is still a part of this answer. Remember, I'm going over some harder problems. If you're kind of like, whoa, that's one of the harder problems we did. And you're right. It doesn't mean the whole final is going to have the hard problems, but if we're going to do some together, I figured we could do those. Be careful. Don't make up rules. Making up rules would be like trying to multiply 2 times 3 and getting 6, and then maybe adding the exponents and getting -1. Ouch, ouch, ouch. Okay, let's get rid of that. That is not right. The bases weren't the same. Instead, you can just do the math. Do the math would be to figure out 2 to the -3. Now that means you're going to flip it and make the exponent positive. So if I flip it, I get 1 over, and then a positive will get you 8. How about this 3 squared? That's just 9. Now be careful, because some of you had this question on a quiz, and you got this step right, but then you messed up the final answer. How do you multiply? It's easy. You just multiply the numerator and denominator. Folks, if you multiply the numerators, you get 9. If you multiply the denominators, you get 8. 9/8. Okay, you just multiply. And then we have a graphing question to boot, the y-intercept. I mean, you could type this into Desmos because, well, you will have Desmos for the final, but it might be just as easy to plug in a 0, something we've done time and time again. Just make sure that you're doing 3 squared first. It's 3 squared. Notice that the 2 out front is saved until the end. So order of operations, the 2 out front is saved till the end. So we get a y-intercept of 0.18. Now, the problems that remain are not just more of the same, but they do kind of go back and touch on the same units. Again, the final is really only those units, 6, 7, 8, 9, and 10.